This is video 2 for the circuits unit notes. Okay, in this one we're going to talk about another scientist who studied electrical circuits, Kirchhoff. Along with Ohm, Kirchhoff helps us understand exactly what's happening to all of the voltage, the amps, and the ohms inside of a circuit. And then with Kirchhoff's, he created two rules or two laws, and they're junction rules, and they help describe the conservation of electrical charge in circuits. And since charge is conserved, the current must be conserved at each junction in the circuit as well. So Kirchhoff's first law. Basically, this one tells us that the sum of all potential differences must equal 0. So what this basically means is that the voltage drop across each resistor must add up to the voltage drop of our power supply. So here I have a delta V for my battery. So this is delta V is going to be 5 volts. And as I look at this circuit here, I have two resistors. This means that the voltage drop across this first resistor and this voltage drop across the second resistor has to add up to give me 5 volts. So what this tells us then, Kirchhoff's first law then, it would say that the delta V minus delta V1 minus delta V2 equals 0, or delta V equals delta V1 plus delta V2. All right, now if we take a look at the current, we're going to have some current that leaves this battery. Now, all of the current that leaves a battery must return to the battery. That's because of conservation of charge and conservation of current. So since all of the current that leaves the battery must return to the battery, that means all of that current stays the same as it flows through those two resistors. So we have Kirchhoff. Now we can go ahead and apply Ohm's law. So for the battery, I have delta V equals I times R. And then for the first resistor, this delta V1, that would equal I times R1. And for delta V2, it would be I times R2. So when we take a look at this, we can see then that all of these currents, I's, will cancel. And I'm left with R equals R1 plus R2. Okay, well, this kind of leads us to the idea of equivalent resistance. This is the resistance of the whole circuit. So these resistors up here, we say that these resistors are series. They're in series. And what series means is one after another or on the same line. I'll say it's on the same wire. So the equivalent resistance, which I'm going to call this REQ, so the equivalent resistance of this circuit would be R1 plus R2. So looking at resistors where they are in series, the equivalent resistance equals the sum of all the individual resistors. Now we can also have power. Power is equal to delta V times I. So I'm going to have some total power being provided by the battery. so many watts. This battery can provide so many watts. And then when I do, I can have power at the first resistor, which would be delta V1 times I. And I can have power at the second resistor, which would be delta V2 times I. And I hope that you can see this. The total power would equal the power from resistor 1 plus the power from resistor 2 added together. So we can take care of all that power as well. And all of this kind of goes with Kirchhoffs' first law. The second one states that the sum of all currents at a junction must equal 0. So a junction is where a wire is going to branch off into 2 or more paths. So I can see that with this circuit down here. Now, once again, we have to apply conservation of charge or conservation of current. All of the current that leaves this battery must return to the battery. That's because of conservation of charge. So when this current comes up to this junction, what that means is that it's going to have to split. I'm going to have a certain amount of current, I'm going to call it I1, that's going to go down through resistor R1, and I'm going to have a second amount of current, I'll call it I2, that goes down through resistor R2. Once these currents have passed through the resistors, they're going to recombine at that second junction, become I again, and return to the battery. Now we say that these resistors are parallel, and hopefully you can see that. They're side by side. And when it comes to parallel resistors, sometimes I like to say they're branching. It's kind of deceptive when they're parallel and when they're not, so you have to be very, very careful about that. So, on to Kirchhoffs' second law. So here we see we have a junction, so I'm going to look at that one. Sometimes they're called nodes. And I would see that I minus I1 minus I2 equals 0, or I can say that I equals I1 plus I2. Now, because of the voltage, here's where it gets a little tricky. The voltage would actually be the same across R1 and R2. So if my power supply is at 6 volts, I would have a potential difference of 6 volts across R1 and a potential difference of 6 volts across R2. The current's different, but the voltages will be the same. So looking back to Ohm's law, delta V equals IR, that means that I would equal delta V divided by R. So this first current, I would have my delta V divided by R would equal delta V divided by R1 plus delta V divided by R2. And this time the delta V's would cancel. So I'm left with 1 over R equals 1 over R1 plus 1 over R2. And again, this time, this R is going to be my equivalent resistance. So for this one, the way we calculate equivalent resistance it equals the sum of 1 divided by the individual resistors, but we have to remember to invert it to get it back into its original, or back to its actual form. Once again, we can also take a look at power. So we got some total power. And, power equals, not power. Delta V times current. So here I'd have power 1, which would equal delta V times I1. And here I'd have power 2, which equal delta V times I2. And because of that, the total power, once again, equals the sum of those powers. So power doesn't care if a resistor is in series or parallel. It doesn't care, because each resistor is going to consume some electrical power. And it doesn't matter whether those resistors are in series or parallel. So the total power will always be the sum of the powers for each individual resistor. Finally, we come to complex circuits. So taking a look at this, I'll let you study that little diagram right there, but notice that resistors 2 and 3 are parallel, and that these are going to be in parallel, or in series with R1. So I can kind of think of this as something like this, where I have my resistor R1. I'll call that resistor RP for the R2 and R3. And we can go through and we can work out all the math for all of that. If I were to take a look at light bulbs, I can replace these with light bulbs such as this. Some questions I may ask you is like, which light bulb would be brighter? And really it comes down to power. Whichever one has the greatest power will be the brightest one. So, for some review, Kirchhoffs loop rules describe conservation of energy in circuits. Energy changes in simple electric circuits are conveniently represented in terms of energy change per charge through a battery and resistor. We call it that voltage. Since the electric potential difference multiplied by charge is energy, remember delta V times Q equals work, and energy is conserved, the sum of the potential differences about any closed loop must add up to be 0. So that's Kirchhoffs' first law. The electric potential difference across the resistor is given by the product of current and resistance. So that's delta V equals IR, so that's Ohm's law. And finally, the rate at which energy is transferred from a resistor, or basically electrical energy into thermal energy, is equal to the product of electric potential difference, multiply across the resistor times the current. That's, again, power. Power equals delta V times I. So that concludes this unit.